Now, up until now, when we've been dealing with our parallel plates, say, imagine we have our two benches again, our two parallel plates. It'd be like if there was a hole in this bench and we just shot the particle through, okay? So it comes in perpendicular with the plate, okay? That's what we've been doing so far. So it's like it just either shoots right across and like hits the other side because it's going fast, or it decelerates and stops, okay? But now what we're going to do is we're going to look at questions where a particle is coming in parallel to the plates. So just like in this example, it's coming in like sideways to the plate, okay? Now, since it's coming in sideways now, it has almost a different type of motion than just going straight up or slowing down. It's going to travel throughout the whole plate, and it's actually going to have projectile motion. Okay? So we're going to have to use our knowledge of projectile motion for these types of questions. So, and then, okay, so here it says, in previous examples, we only consider problems where the charged particles are moving parallel to the field. Therefore, if force and distance are parallel to each other, work is being done and particles accelerate. Recall, though, that if a particle is moving perpendicular to the force, no work is being done, and therefore the particles maintain uniform motion. So now, when we did projectile motion, there was a very specific type of, we could summarize kind of what was happening. So if an object is projected outward, okay, and say these are its different spots that I just measure, what can I say about, yellow question, what can I say about the object's horizontal velocity at this point? Let's just say it starts at speed of 5 meters per second. So what would its horizontal velocity be at that point? 5 meters per second. So my v of x is 5 meters per second. Okay? What would its horizontal velocity be at this point? Pardon? 5 meters per second. Green question. Explain to me, Lisa, why you made that conclusion.
Because it keeps going at the same velocity and at the same speed, but gravity just pulls it down.
Okay, so then, can you describe to me what would be different about the vertical vectors? Okay, acceleration due to gravity. So what would my vector look like here for my downward velocity? Okay, that's my acceleration due to gravity. But it would be really small here, right? My vector, my down vector would be very small. At the very beginning, it would be 0. V of y is 0, right? Because it has no downward motion yet. Okay? Like right at the very beginning. Initial. Okay, good. And then as I go down, it gets larger. Okay? But your horizontal always stays the same. Okay? So that's just kind of that, remember, going back to our projectile motion. Okay, good. Right on. You guys are with me. All right, so now we're going to take that information and apply it here. So we're going to have to break down our information into horizontal and vertical information. Now, what carries the same across both? There's a variable that carries the same across both. Time remains the same. So if you can find time horizontally, you can apply it to vertical. Very good. Okay, so let's read this. The drawing shows an electron entering the lower left side of the two parallel plates and is exiting at the upper right side. The initial speed of the electron, so that's our horizontal, because we know that our initial vertical is 0, is 7 times 10 to the 6 meters per second. The parallel plates are 2 centimeters long and separated by 0.15 centimeters. Okay, so let's separate our information into horizontal vertical information. So, and I'm just going to note here, horizontal is uniform motion because of what you guys just told me. And vertical is accelerated. Now, this is going to be different than Physics 20 acceleration because we are going to assume that these subatomic particles are so small that the force of gravity is actually negligible. Okay? So when we think of F net, what are the forces acting on this are Fe, our electric force, and Fg, but it's negligible because it's so small. Okay? So when we think about your F net, if you're needing to use like F net equals m times a, you assume that your electric force is your F net for these small subatomic particles. Okay? All right. So now let's put down what we know. We know our velocity here is 7 times 10 to the 6 meters per second. And I know that's for my horizontal because my vertical starts at 0. My distance, what's my horizontal distance, Maddie? How would I find, it gives it to me in my diagram. 2 centimeters, yeah. Which is 0.2 meters. What do I know about this side? My vertical distance. What's my vertical distance, Kim? Vertical distance. So it's like, think about, the object went this far horizontally, but it went this far vertically. So our 0.15 centimeters. So 0.0015 meters. And our VI is 0 for our vertical. All right. And we are trying to find out overall our electric field strength. Is our question. So let's just, I might just map out how we're going to do this for you. Because with these questions, you're going to have to kind of work backwards quite a bit. So what we're going to do, we're going to look for electric field strength. I can't use K, Q1, Q2, blah, blah. But I can use my Fe over Q. Well, I wasn't given my force, but I can find Fe using F net equals m times a. Okay? But I wasn't given a, so I need to find a using an acceleration formula. Okay? So it's like, here's step 1, here's step 2, and then here's step 3. Step 1 will involve a couple calculations because we have to find time first, etc. But that's kind of overall what we're aiming for. So on this side, we can find time. So T is equal to D divided by V, 0.02 meters divided by 7 times 10 to the 6 meters per second. So T is 2.857 times 10 to the negative 9 seconds. We can take this information over and use it for our vertical side because time is the same for both. And so I'm going to try and find acceleration on my vertical side so that I can use that in my F net equals m times a. So then you look at your data sheet and see what type of acceleration formula uses those variables that you can find acceleration with. So you know d, v1, t, and a. So we'll use our d is equal to v1 times t plus half at squared. v1 is 0, so I can just eliminate that. And we'll solve for a. So a is equal then to 2d over t squared. So 2 multiplied by 0.0015 meters, all divided by 2.857 times 10 to the negative 9. And make sure that t is squared, that you square that bottom fraction. So then A is equal to 3.67 times 10 to the 14 meters per second squared. So that was step 1. We found acceleration. So now step 2, F net is equal to Fe, because of the assumption we made prior, is equal to mass times acceleration. Now this is the mass of an electron, so you find that on your data sheet. 9.11 times 10 to the negative 31. And we put in our acceleration, 3.675 times 10 to the negative. No, wait, I wrote down the wrong number. No, I didn't. Negative 14. There it goes. So our Fe then is 3.3479 times 10 to the negative 16 newtons. So now that is step 2 done. But our whole question was to find our electric field strength. So now we take that value and divide it by Q, which is the charge of our electron. So step 3, we want to find electric field strength. So that's 3.3479 times 10 to the negative 16 newtons divided by 1.6 times 10 to the negative 19 coulombs.
Does it matter if it has to be negative or not? Even though your electric field strength is a absolute value, since it's not
Like to make this a negative?
like the Q, because it's an electron.
Oh, no. But then when you are writing your final answer, we'll look at the direction of the plates and say up or down for the direction. Yeah. So our electric field strength is 2.092, etc., times 10 to the power of 3 Newton coulombs. So then our final answer, we need sig, digs, and direction. So 2.09 times 10 to the 3 Newton coulombs. Now let's look back up at our original diagram, and which way is our electric field strength going to be going. If this is positive, this is negative, it always goes away from the negative, positive, sorry. So the electric field strength is always going to be going which way? Down. So it's going down.
We're back down to.